Hello and welcome to another installment of Corman Does Chemistry! Alright. I think we'll start with a little cute picture. It's kind of hard to see since the snow blends in with the other snow, but hopefully you can see the dog frozen next to a fire hydrant. Thought that was funny, leading into a lesson on entropy and free energy and enthalpy. Okay, maybe not. Alright, sorry the notes look weird. Did something different with it, but I do not like it. However, it will do for today, especially since you have the notes in front of you anyway. So just to remember from last year, entropy is a measurement of how chaotic or random or disordered the particles are in your system that you have. So really what we're looking at is not just a system. We're not just going to say, oh, I have a glass of water. What is the entropy of that? What we're going to do is say, I have a glass of water that turns into ice cubes. What happened to the entropy? Did it increase in its disorder or did it decrease in its disorder? And that's the part of it that we're going to be mostly concerned with, is thinking about whether or not the particles have become more chaotic or less chaotic as it goes from the reactants to the products. And so that's what you need to be thinking about. Usually the easiest way to do that, the most straightforward thing you're going to be looking at, is whether or not your particles, or what the phase is really of the particle. So if it's going from a solid to a liquid, solids have less movement than liquids. So since it's going to a state with more movement, you're going to have more entropy. Okay, that's essentially what that means. Now, one thing we do need to know, and hold on, my computer is not up on my screen. All right. One thing that we do need to know and be thinking about is what the sign is of delta S. So somewhere on your paper, probably on the very front, if you go to the very front page, and put this in here, let's make a list of what all the signs mean at the very top on the front page, because you have to know these 6 things. You have to know that a positive delta H means endothermic. You have to know that a negative delta H, so this is both enthalpy, means exothermic. You have to know that a positive delta S means the particles have become more disordered. So that would be, an example of that would be like a solid going to a liquid going to a gas, a solid going to a gas. Those are all examples of becoming more disordered. Less disordered would have a negative for its delta S sign. So if it has a negative delta S, then that means as the reaction took place, the particles became less disordered. So that would be liquid becoming solid, or liquid gas becoming solid. What other combination do we have there? I knew there was one more. Gas becoming liquid. Okay, so those particles, if you think about gas particles, they're moving around like crazy. If they go to liquid, they're much more ordered in their position. If they go to solid, they're much, much more ordered. And this is true of both chemical and physical changes. We're also going to be putting on this list, so let's go ahead and write it now and then we'll come back to it, what a positive delta G and a negative delta G mean. So just put those on there for now and then we'll come back to those. All right, so back to entropy. So you see that there's an equation here for entropy. If you look at your delta H equation, there's one that looks just like this. Essentially, if you know the entropy of all your products, the standard entropy of your products and all the reactants, you can just subtract them from each other and you will get the overall entropy change. Those entropy values have to be given to you. So you see here in this problem, they are giving us entropy values. So you're really just a matter of plugging in some values is what these entropy changes come down to. So we're going to start with the products. Okay, so if we look at our balanced equation, the only product we have is CaSO4, and there's only one of them. Just like with delta H, we have to account for how many we have. So you have one of those, so that'll be 106.7. And then that's all of the products, minus now the reactants. So I have one CaO, so a CaO according to the problem has an entropy value of 39.7, and I have one SO3, it has an entropy value of 256.6. So now I've got to plug in my calculator, watch your order of operations, and you should end up with negative 189.6. The unit is joules per Kelvin. If you notice here, the unit started as joules per mole Kelvin, but the mole part of the unit falls off because we were using the coefficients for this. Now in this equation, all the coefficients happen to be 1. But if there had been a 2 in front of, say, CaSO4, then you would have multiplied right here by 2. So although it's not seen, we still did it. We multiplied by 1, and it wasn't really changing the answer. Okay, so calculations of entropy are usually pretty easy. I mean, they have to give you all the reactant and product entropies, and then you just subtract the products all added together minus the reactants all added together. And this one, because you have a negative delta S, that's telling you that it became less disordered. And we actually already knew that that sign was going to be negative, because if you look up here in the equation, you had a solid and a gas becoming all solid. So because you had some gas there turning into a solid, it was more, I'm sorry, it's the wrong word. It was less disordered. Okay, it was becoming less disordered. Now, if you'll take a look up here, there's 2 more things. There are going to be instances where in your equation, right here on where they tell you your phases, they might all be gases, okay, or they might be all, probably the only time you're probably going to see it is if they're all gases. So how do we tell entropy if the phase is the same? Because that's usually how we decide if something's becoming more disordered or less disordered. So the first one says particle solutions have higher entropy than solids. So let's say you had a substance like NaCl. Your equation was NaCl solid being placed in water becomes Na plus, which is aqueous, and Cl minus, which is aqueous. You have solid becoming aqueous. That means it's becoming more disordered. Okay, those particles are more disordered. Then if you don't have even that, let's say all the phases are the same, like it's all gases, then what we're going to do is look at how many moles we have. Because the more moles you have, the more chaos you have. Think about Disneyland. When it's crowded, there's a lot more chaos than when it's empty. So let's say you had an equation like this. You have 2A gas plus 1B gas becoming 1C gas. Okay, so all gases, we can't tell entropy based on the phase, but we have 3 moles turning into 1 mole. So that is becoming less disordered. Okay, less disordered. Those particles as 1 mole don't exert as much chaos. So the entropy change for this one would have been negative. Okay, so we will practice some more of those with our problems on Monday. All right, so that is entropy. That should be everything we need for entropy for now. So you're going to have to do 2 things with entropy. Calculate the delta S and be able to predict the sign without a calculation. So you should be able to look at the equations and use these things up here to decide. Okay. All right, there's that again. All right, so Gibbs free energy. Now what Gibbs free energy is a measurement of spontaneity. We learned in the equilibrium chapter that if our K value is greater than 1, then we have more product than reactant, and our reaction is spontaneous. This is another way to figure out spontaneity. You can actually calculate delta G a couple of ways, and once you know your delta G, you can tell whether or not your reaction is spontaneous or not. You can see on your paper that it says if delta G is negative, that means the reaction is spontaneous. If it's positive, that means your reaction is non-spontaneous. And if your delta G is negative, it means the reaction is at a dynamic equilibrium situation. We will get into that part a little bit as we're actually studying problems in our review of thermodynamics. For now, we won't see too much of that. I'm not sure. I may have a problem or 2 for us to sort of assess that part of it. But for now, we're just going to focus on the positive delta G and the negative delta G. So if you go back here, let's go ahead and put these in. So positive delta G means non-spontaneous. And a positive negative 1 means spontaneous. So a positive means non-spontaneous, and a negative 1 means spontaneous. All right, you have to know those 6 things. Have to. Okay, make yourself a note, put a big star on it, circle it, highlight it, do something to it. It is important. Okay. All right, so back to our Gibbs free energy. So there's an equation just like delta S and delta H have that simply says that if you're given the Gibbs free energy values for your substances, then all you have to do is subtract products minus reactants. It's a very easy way to do these problems if you're given that information. So we're going to talk about delta G. We're going to do our products first, 2 SO2s and 1 O2. Once again, we're going to use the coefficient. So for 2 SO2s, it says SO2's value is 300.2. Okay, and then we're going to add to that the value for O2. Now you see O2's value is 0. You remember with delta H, pure elements were 0, and that is true on delta G as well. So somewhere on your paper, make yourself the note that the delta G value for pure elements is 0. It's not 0 for entropy. Pure elements have entropy. Even if it's a pure element, they have chaos, they have disorder. But for this one, for delta G and for delta H, they will always be 0. And then we're going to subtract all of our reactants, which is 2 of the SO3s. So we're going to have negative 371.1. So, and we end up with a delta G value of 141.8 kilojoules. Now that delta G value numerically tells us some things, but just the sign of it tells us that this reaction is not spontaneous the way that it's written. So if you were to try to do this reaction as is, then we would not end up with a spontaneous reaction. Okay? Questions about that? If you have anything, remember, just kind of keep your notes to the side, and then when you email me, you'll have an opportunity to tell me that. All right, the relationships. Now here's where your signs come in. This is where you have to know your positives and negatives. Some of the problems on the AP test are going to be math-oriented. Some of them are going to be concept-oriented. Okay, so this is the concept part. I already told you to highlight or something those 6 pluses and minuses, that you absolutely have to know those. The other thing that you absolutely have to know is this part right here. You have to understand that all reactions are looking for 2 things. They're looking for a negative delta H, so they want to exert as little energy as possible, but they also want a positive delta S. They want to be as chaotic as possible. That may seem a little contradictory, but I can actually use teenagers as an example of this. Most teenagers want to exert as little energy as possible and be as free as they possibly can be. Like your bedroom at home is much easier to keep it messy and chaotic. It takes a lot less energy on your part to leave your room messy and chaotic than to keep it clean. Okay, so it's kind of that same principle. We also have this fantastic equation that relates all 4 variables to each other. You have Gibbs free energy is equal to the enthalpy minus, this is temperature, and then delta S. And this temperature has to be in Kelvin, okay, because of the temperature units on delta S and delta H, okay, actually on delta S. So here are your combinations. You've got them written here in front of you and you can read. Essentially, here's the deal. If you have a negative delta H in your situation, so you read the problem and figure out that it's an exothermic reaction, that is a good thing. So I want you to start to use my silly notation of smiley faces. Those of you that were in my class last year did this. I'm not sure if Ms. Pickens did it as well. But you have a smiley face if it's a negative delta H, okay? Because that's a good thing. If you see a positive delta S, that's a good thing, okay? So if we look at the first example, we have a negative delta H, that's a good thing. We have a positive delta S, that's a good thing, okay? So you've done your problem. This is not going to be given to you, by the way. You're going to have to figure out the signs of the delta H and the delta S. But after you've figured it out, you now have a negative delta H and a positive delta S. That's both good. If it's good and good, this reaction is going to happen, and it will be spontaneous all the time. This isn't always spontaneous because it got everything it wants, okay? For the second set, positive delta H is bad. Negative delta S is bad. If this reaction is not getting anything it wants, it will never be spontaneous, regardless of temperature, regardless of this factor that's also in the equation. It will not be spontaneous. But where we get into the area, so always spontaneous, never spontaneous, but where we get into a gray area is what if it has a negative delta H, which is good, and a negative delta S, which is bad. So it has one good and one bad. In that situation, that's where temperature plays a part. So if you have one good and one bad, then the temperature is going to be your deciding factor, okay, it is temperature dependent. If they are both negative, then low temperature is where you will get your spontaneous reactions. Okay, I tell my students to remember negative, negative, low. Okay, so if you have a negative delta H and a negative delta S, then low temperatures are where we will get spontaneous reactions. Okay, for the positive delta H, that's bad. For the positive delta S, that's good. So again, we have a good and a bad. If it's a positive and a positive, then it's spontaneous only at high temperature. So I tell my students to remember, if it's positive and positive, it's high temperature to get a spontaneous reaction. You have to learn that. You have to know that. They are going to ask a ton of conceptual questions related to that information. And to be able to do what we just discussed there, you have to be able to read a passage and be able to tell what's happening, whether or not it's endothermic, exothermic, whether or not it's more disordered or less disordered. You'll have to tell the signs for those, so that's where the memorization of the 6 come in. Then you'll have to be able to apply the part here where it says this is what they want. You have to be able to look and see and remember that a negative delta H is a good thing, a positive delta S is a good thing. So as long as you know all of that, then you'll be able to answer these questions with relative ease. Okay. Sometimes we're also asked to calculate with this equation. Okay, we'll do some practice with that on Monday. Really all you have to do is make sure all your units match up. Okay, most of the time delta H is given in kilojoules per mole and delta S is in joules per mole Kelvin, so we will have to make those units match up. And then obviously if you do a calculation, then you're going to figure out whether or not it's spontaneous or not based on the sign of the calculation. So we'll practice some of that next time I see you, because that's a big part of why we're doing this lesson at home. All right, the last thing that's on here, and again, we're going to see this more in some example problems, and I'm going to use that as a way to look at it, but you can actually also calculate a relationship between equilibrium and delta G, all right? These equations relate our equilibrium constant. This is our equilibrium constant. And then if you remember, this is our equilibrium constant when we're not sure if we're at equilibrium. Okay, so when we're not at equilibrium, we can use this equation. So if we are just given like, oh, here's all your concentrations of where you're at right now, you can actually plug those into a Q and plug that in with the ln and take the r and the t and add it to the delta G standard. And you can figure out what the delta G's are at non-standard conditions. That's the difference between this delta, is that spelled right? Yes. This delta G and this delta G. This one has that little degree symbol. That means it's at standard condition. So we will see that equation as well come up. I just wanted to introduce it to you and let you know that it exists. Okay? So here's what I need you to do. I need you to send me an email. In that email, first thing I need you to do is to tell me what are the things you need to have down to be successful at the conceptual questions. Okay, so what is it that I said in our lesson that you need to learn to be successful at the conceptual questions? The second thing you need to do is send me any questions, comments, anything you're not sure about, anything you'd like me to expand upon, so I can format that and get it ready for Monday. And then the third thing, ooh, something fun. Send me a picture of something. I don't care what it is. That seems frightening. Okay, well, I do care what it is. Something appropriate and good for school that wouldn't be offensive to anyone. All right? Okay, so I will speak with you guys later, and happy entropy.